Hello and welcome back. In this lesson, we are going to look at energy function. And I thought this would be important to first understand before we look into the Hopfield network in the next video. Hopfield network. And if you are already familiar with machine learning a little bit, or if you are not, what we are using this function is similar to a loss function. And how the idea is we are trying to check if whatever output we are getting it matches the the actual ground truth or pattern or the uh, output that we are expecting, and energy function is a way that Hopfield network checks that. And energy function then is given by this equation: E of A is equal to minus 1 by 2, and then we have A transpose W dot A minus B transpose A. Now in this particular A is the activations or um, activations that we calculate, or we could say that these are the state vector of neurons. And then W is, as usual, we know this is a, in case of Hopfield network, this is a weight matrix. We already know that weight matrix, but in case of Hopfield network, this is symmetric. And in addition to that, the diagonals are zero with zero diagonals, and this is the bias term, and this is often zero, right? So with that equation in mind, what we are going to try and do is think about creating an example for a 2D case, and then we'll try and create an example for a 3D case. And for that, what we'll do is we are going to assume that our W is, in 2D case, it is as follows. It is 1 0 1 1 0, and note that we have the diagonals are 0 as we said here. The bias we will set it to 0, and the value for the matrix A, just to generalize this, we are going to say that this is A1 A2. Okay. Now what we are going to do first is calculate W dot A, and that's going to be 0 0 1 1, and then A is going to be A1 A2, and this gives us A2, and here we get A1. Next, what we are going to do, take A transpose and dot that with above output. So A transpose would become A1 A2 horizontal, and then we have this A2 A1 which is vertical, and thus if we perform the dot product, we get A1 A2 plus A2 A1, that essentially is 2 times A1 A2. And this is sort of the general equation. I'm going to write that down up here, where we'll say that when we calculate E of A, that is 2. So when we plug into that above equation, what we get is minus 2 times 2 A1 A2, and this would get us uh, these 2 cancels out, and we get minus A1 A2. And another way to think about it when we are plotting in Desmos is we can think of this as energy as shown on the z-axis, And then we have A1, A2 shown on the y-axis. So in the Desmos, we can plug in this equation. Likewise, if we think about the 3D case, our W could be something like this. We have the diagonal, which is zeros. Then off diagonals are values of 1. And again, we set the bias to 0. And A, because we are in 3D case, we have A1, A2, and A3. Again, we perform the same dot products. First, we try and calculate W dot A, that is going to be equal to 0, 0, 0, 1, 1, 1, and here we have A1, A2, A3, and then what we can do is perform this multiplication. So A1 times 0 is 0, and then 1 times A1, A2 is we get A2 plus A3, and then in the next row we get A1 plus A3, and the last row we get A1 plus A2. Next, what we do is we are going to use the A transpose and dot that with above vector that we get, and A transpose, when we flip that around, we get A1, A2, A3, and then we have these values A2 plus A3, A1 plus A3, A1 plus A2, and so now when we perform the dot product, what we get is the following: A1 times A2 plus A3, then we have plus A2 times A1 plus A3, then we have plus A3 times A1 plus A2, and if we multiply all these terms out, we get A1 A2 plus A1 A3, then we have plus A2 A1 plus A2 A3, then we have plus A3 A1 plus A3 A2. And now if we look at this A1 A2 and this A2 A1 is the same, so we can say 2 A1 A2, and then if we look at A1 A3, we see that they are also occurring 2 times, so we can say 2 A1 A3, and finally A2 A3 is also 2 times, so we say 2 A2 A3, and this then we can get the 2 as common out, and then in the parentheses we have A1 A2 plus A1 A3 plus A2 A3, and when we put this in the equation to calculate E of A, that is the energy in the 3D case, we would have minus 1 by 2 into 2 times A1 A2 plus A1 A3 plus A2 A3, and then this 2 cancels out, and so what we are left with is minus A1 A2 plus A1 A3 plus A2 A3, and what we can say when we are plotting in Desmos, because we can only plot 3D, we already have 3 A1 A2 A3, so to be able to plot, we cannot plot 4 dimensions to what we are going to do is set A3 is equal to minus 1, just for the sake of plotting purposes, and so what we have in here is minus A1 A2 minus A1 and then minus A2, and if we And so in the Desmos, when we plot, we'll think of energy on the z-axis, so we can see the peaks and values of the surface. And then we can, as before, we can say that a1 is x, a2 is y, this is x, and this is y. So that is our equation for energy, that in the case where we have this w, and we set the a3 to -1 in the 3D case. Now that we have both of our equations set up, for the 2D case, which is this one, and for 3D case, which is this one, let's go to Desmos and try and plug this in and see what the surface looks like. And for that, we can go to desmos.com. Already I am here, so desmos.com, and in the graphing calculator, we can type z is equal to -xy, which is what we have found here. And this is the nice blue surface that you see. This is the energy surface, and what we are trying to see here is that uh, on the z-axis is represents the energy, where uh, this uh, we have like this curve that comes down and then goes back up. So if energy is high, which is up here in the peaks, then the neurons need to change the values of A. So it has to change the values that would be in A to bring the energy down to minimum. And if the energy is down, just as we see here in the valleys, in that case, then the neurons need not change the values that are for those particular A's. And here we can see that some of these data points shown here, the dots, they are in the values, which represent that they are okay. So we can see if I can stop spinning. All right. So that's the idea with the. So I think I will just upside down. So that's the idea with the 2D case. Now in the 3D case, here it says 3D, so probably should change that. In the 3D case, remember this was the equation we had, minus in the parentheses xy minus x minus y, and that's what we have. The shape looks similar, but then we can also see that there are points that we can show where they fall on the energy curve. And remember that here the A is set to -3. In the previous case, where we have these values a1, a11 -1, so the 1 and 1 is the x and y, and then the last -1, that's for the energy, that's the z coordinate. Likewise here, 1 and 1 is for the x and y, and then the last coordinate z is for energy. It is not for a3. That is something we need to remember. Alright, so what we can try and do is try and see if this really is the case that we see here. For example, in the 2D case, uh, let's pick the point A. So what we have for A is 1, 1, that is the value for x and y. So what we can do is come down here and try and calculate the energy for that. So if we say E of A is equal to minus a1 a2, and in this case we are saying that a1 is 1 and a2 is also 1, a2 is also 1, and so what we get in the output is E is -1. And if E is -1, then that's a good thing, that energy is negative. So if we change the color of this particular plot dot, and let's say change it to maybe a green, and then look at the point in here, we see that it's low energy state, as we can see, the green dot A is in the value right here. If we look at, if we change the values of A to -1, so if we say E of A is equal to -1, -1, then again what we get is -1 is +1 into minus, so we again get -1. So this point B should also be in the valley of the of that particular energy surface, and we do see that is the case. So both of these points are in the valley. Now C and D should have values that are above, that are positive. So if we go back and try 1 -1, so if we try the value of A as 1 and the value of A1 as 1 and A2 as -1, what we get is +1 in the output. And so there we are saying that the energy is high, and that is therefore we see that those data points, that one is here. So let me just let's get the second one also. So E of A, and here we say that, well, minus A1 is -1 and A2 remains 1. So again in this case as well we get a +1 in the output. So both C and D are here up in the energy plot, where they are on the rising side, so not in the valley, they are along the peak. And therefore we can say that if that is the energy, then the values for neurons need to be changed. In Hopfield they are usually flipped, and to get the um, energy to a lower state. Let's calculate the value of energy with A1 as 1, A2 as 1, and for that we can plug those values right in this equation, where we can say energy E of A is equal to minus, and this is 1 times 1 minus 1 minus 1, so what we get is -1 minus 2, and so that is minus of -1. So in the output we get +1. So that's high energy. And if we try to look at this point A, which is in green, it should be somewhere along the higher side and not in the valley. But it does look like it is in the valley. It's on the saddle point. So it's on the saddle point, not in the valley, it's on the saddle point. So maybe there's still scope to improve that further and bring the energy further down. If we look at the point that's down here, which is, let's say, the point D, as you can see, it's pretty low in energy, where we have the A1, A2 as -1, -1. So we can plug those values in here and see how it works out. So this is -1, -1, and then we have minus of -1, and that calculates out to this becomes +1, this becomes again +1, this becomes +1, and so what we have is -3. So that's a low, pretty low energy that we have, and that's the point we see down here in the valley, and so on for the others. So what we are uh, getting out from this is, in the Hopfield network, when the values for A are updated in each of the iterations in the recurrent network, the network also checks for energy. If the energy of a particular, if the energy is high, that is positive, if it's in the peak or the saddle region, if it can be improved further down to valley, then it changes the values of A, and the values of A, as we'll see in the next video, can be flipped, and that affects the energy levels. So I think that was it for this video. Before we end this video, one last point. Probably wondering why we calculate the energy this way, where we have W transpose A. W transpose A, we already are familiar with this. This gives us sort of the magnitude or uh, local values for each neuron. And when we perform a dot product with A transpose, uh, this vector sort of gets uh, collapsed or summarized into just one scalar value when we do A transpose. So uh, performing A transpose with W dot A uh, uh, can give us an overall picture of all the neurons in that layer, how they are affecting the energy for that system or for that network. So that was it for this video. If you still have any questions on this topic, please feel free to post them in the comment section below. I hope to see you all in the next video where we discuss the Hopfield network. Bye for now.